Hello guys, today we're going to be doing further mathematics, probability and statistics, paper 4142 of the May-June series of 2021. So let's begin. The first question is an inferential statistic based questions where we have a sample size of 7. Okay, so here we have 7. So n equals to 7. 7. That's the first piece of data that we need to know. Population mean of X is mu, test at the 10% significance level. Null hypothesis mu equals 8.22 against the alternative hypothesis mu lesser than 8.22. So they've already stated out our hypotheses, so we don't need to specify that. Now to calculate when we're trying to perform a test, we need to know a few things. Firstly, we need to compare the test statistic and the critical value. Critical value can be directly derived from the list of formulae here, and given that the sample size is 7, you can find the degrees of freedom, which is 7 minus 1, which is 6, and you can see degrees of freedom of 6 appearing over here. Okay, so that means that we are using critical values for the t distribution. So we've already narrowed down where the critical value would be. Next, we have to find the test statistic. To find the test statistic, there are a few formulas that you need to apply so that we can find it. So test statistic, we're going to denote it with t because we are using values in the t distribution, and this is equal to the sample mean minus the stated mean whole divided by root of S2 divided by number of terms. This right here is the formula to find the test statistic. So the pieces of data that we do not know yet are the sample mean over here, S2. These are the two pieces of data we don't know. As for mu, we've declared it as 8.22 in the beginning in our null hypothesis, and n is 7. Okay, with that being said, we need to calculate sample mean and S2. So let's first calculate the sample mean. Sample mean is equal to, so how would we calculate the sample mean? It is just the sum of all the x values above divided by the number of terms n. So let's calculate the sample mean. It will be 8.26, or let's just add them up first. 8.26 plus 7.78 plus 7.92, 8.04 plus 8.27 plus 7.95 plus 8.34. This is equal to 56.56. Okay, so let's just state our sum of x values, and this is going to prove out to be useful to find S2 as well. 56.56. Okay, now that we have this over here, 56.56, which is the sum of x, should be divided by n. N is the sample size, which we've declared as 7 as stated in the question, and so all we need to do is divide this value with 7, which is equal to 8.08. So 8.08 is our sample mean. So let's just write down here 8.08. Now that we have the sample mean, the one thing that we are yet to find is the S2, which is the unbiased estimator of the variance. How do we calculate S2? So there is another formula for that, and that is S2 equals to 1 by number of terms minus 1 multiplied by sum of x squared minus sum of x the whole squared whole divided by number of terms. Alright, so this is one formula that you can plug in. The other formula to find S2 would be to find the sum of bracket x minus x mean whole squared. this divided by number of terms minus 1. So this is the other formula we can use. So Cambridge normally expects us to use the first formula. However, at times they may already give this value, and that's where we use the second formula. So it is better known to use this formula. So using that, we need to first, to get S2, we need to find the value of sum x squared. So the value of sum x squared needs to be found to calculate S2. So what is this sum of x2, sum x squared? It means that we're doing x squared and then adding up all the values, which means that we're not adding up all the values and then squaring, we're squaring all the values and then adding them up. So it's 8.26 squared plus 7.78 squared plus 7.92, and this just goes so on until we've squared every single x value. And lastly we have 8.34 squared, that is 457.275. so let's write that down right here, 7.525. okay, now that we have sum x squared, we need to calculate S2. S2 is equal to, now I don't need to write down exactly what I need to plug in the values for. Like I don't need to write 1 by 6 bracket sum x squared and all, because it's already stated, but for this case I will do it. So n minus 1 is 6, and over here we have 457.525, and this is subtracted with sum of x squared, which is just 56.6 squared divided by number of terms 7. Right, so this step not too necessary when we've stated the formula, but it is good to mention it, so let's just do it. And now that we've done that, we can just do 1 by 6 multiplied by our answer. I've saved the answer as 457.275, and this is subtracted with 56.56 squared divided by 7. This is equal to 0.04503 recurring. So this is the value they expect us to write, but in our calculations we're going to be using 1351 30,000. So let's write 0.04503. Yeah, this should be enough. It's not necessary to mention the fraction, but we are going to use this fraction exactly to answer our questions and to find the test statistic. Okay, now that we've calculated S2, we have all the essential information needed to calculate the test statistic. So T is equal to, now we need to write sample mean, which is 8.08, minus the stated mean, which is mu, which is 8.22, this is whole divided by the root of S2, which is 0.04503. This is divided by the number of terms, which is 7. Okay, so with that we can solve our final test statistic. So plug in the values, root answer by 7 is equal to negative 1.745. So we can write here negative 1.745. Okay, so whenever we have a t distribution test and we get a negative test statistic value, just remember that we convert it to positive. We look at the absolute value, because, well, some test statistic formulas can be written as the absolute value of this, right? So in reality it is the absolute value of this, but we don't specify that in the formula itself. We just consider the formula to be like this. We don't put the absolute value when considering the formula, and then we convert this to positive, right? So now we're going to be comparing the critical value with 1.745. We don't compare with negative 1.745. The only time where the test statistic, a negative test statistic, is compared with is in Wilcoxon signed rank tests. Okay, and this is our test statistic. Our critical value is, well, given that this is a one-tailed test, because we are looking at all mu values that are less than 8.22, it's going to be a 1.1 tailed test at 10% significance level. So since it's one tailed, you can do 1 minus alpha, where alpha represents 10%, not 10%. If you want to represent alpha as 10, we can use 1 minus alpha by 100. Okay, so this is when alpha equals to the integer value here, and this is when alpha equals to the percentage value. So 1 minus alpha gives us 1 minus 0.1, which is 0.9. That is the p-value. As for degrees of freedom, it is number of terms, which is 7 minus 1, which is 6. So when you look here, degrees of freedom 6 for 0.9, our critical value is 1.440. Okay, so 1.440. And a good additional step to mention would be to show the deriving of your critical value, which is t, and then we open a bracket and then we put here the degrees of freedom, which is 6, comma, then we put in the p-value, which is 0.90. Alright, so this is a good deriving step for the critical value. Not necessary, but it is good to put it. Right, now for the last step, test statistic and the critical value must be compared. So over here you can see that the test statistic is a little greater than it. So whenever the test statistic is greater for an inferential statistics or chi-square test, we reject H null. So let's write reject H null. Okay, whenever we reject H null, there's a certain structure that we follow. That is, there is sufficient evidence to suggest that, and then we write our alternative hypothesis. Okay, so this is structure whenever we reject H null. So that is, there is sufficient evidence to suggest that. Then we insert our alternative hypothesis. So our alternative hypothesis says that the mean is less than 8.22. So we write suggest that the mean is less than 8.22. That's the first question's answer. And the B part, state the assumption necessary for the test in part A to be valid. So whenever we have a test, we ought to always assume that the population is normally distributed. So population is normally distributed, or you can write over here underlying data's distribution is normal, right? Both ways are considered correct. Choice is yours which to do. They usually like having the word underlying here, so I prefer the conclusion too, but either would be fine. Okay, moving on. Now we have here chi-square tests. So driving school employs 4 instructors to prepare people for the driving test. The allocation of people to instructors is random. For each of these instructors, the following table gives the number of people who passed, number of people who failed their driving test as well. So have here pass, fail, then instructor A, B, C, D, and then the totals. Okay, now them giving the totals is a big boost for us, because normally we had to calculate the totals ourselves, and they just made our process much less tedious. So calculate at the 10% significance level whether the success in the driving test is independent of the instructor. Okay, so whenever we start a test, I'd like to mention the null and alternative hypothesis. So I mentioned them in blue. So H null. So what will H null say? H null will say that success in the driving test is independent of the instructor. Okay, so we can write over here success in driving test is independent of the instructor. Right, that's the first one, which is the null hypothesis. Then there is the alternative hypothesis, which just is the opposite of H null, which says success in the driving test is, well, dependent on the instructor. So here we have success driving test is on the instructor. Let's fix that. Okay, so that is just how you form our hypothesis. This is the key to every single test. Moving on, whenever we have a chi-square test, we need to calculate the expected values. Then only can we calculate the test statistic. So how do we calculate the E values, which is the expected values? So whenever they give us a row and column based chi-square test, all you need to do is use the formula, which is EI. Alright, I'll explain exactly what the formula says in a minute. So EI equals to the row total multiplied by the column total whole divided by the grand total, which is 400 in this case, but just keep it there. Yeah. Okay, so what does this thing mean over here exactly? So we'll write fine. So we're going to be assigning each value in this table with a number from 1 to 8. I'd like to assign from row by row. So 1, 2, 3, 4, 5, 6, 7, 8. Okay, these are the observed values. These are the 8 observed values. Remember, the totals don't count as observed values. Okay, so using the observed values, we can label them from numbers 1 to 8. So when I say 07, it means I'm looking at the observed value of the 7th cell, which is 41. When I say 01, it means 72. 05 is 33, and I think you get the concept. Fine. Now to calculate the expected value of EI, meaning I equals to 1. When I equals to 1, the expected value of the first cell, that's what we're trying to calculate now. So let's calculate E1. That is the row total of the first cell multiplied by the column total divided by the grand total. So what's the row total of the first cell? 234. The column total is 105 and the final grand total is 400. So our test statistic becomes 61.425. Right, so that is our first expected value we found. Next we need to find E2, and similarly we need to do for all 8 values. So the row total remains the same for E2, however the column total changes, and the column total for the second column is 76. So our expected value becomes 44.46. Right, so now to find E3. E3 is equal to, right, so to calculate E3, it would mean the row total 234 times the column total, which is 93, whole divided by 400. That is 54.405. Okay, finally to calculate the last expected value of this row, E4. That is going to just change the column total because we are looking at all the values of the same row. So the row total doesn't change, and we have an expected value of 73.71. Right, so that's the expected values for all cells in the first row. Moving on for expected values of 5 to 8. So let's calculate E5. Now our entire formula changes because, except for the grand total, because now the row changes to 166. The row totals become 166. Column total resets back to the first one, which is 105. And now our expected value becomes 43.575. Okay, next up we have expected value of the sixth one. This time the row doesn't change because we're looking at all the rows of this, all the values of the same row. So this time the column total becomes 76, and you have your answer 31.54. Right, so we found the expected value of these 6 ones. Now to find E7 and 8. E7 equals to, now the column total changes to 93, and row total stays the same. Grand total stays constant for the entire calculations of all E values, and we have 38.595. Okay, and finally E8. Now what is E8? Row total stays constant as before. Column total changes to 126, and we have here 52.529.29. Okay, so just one thing I need to state: when you're labeling numbers 1 to 8, you can label them as 1 2 3 4 5 6 7 8. You can label them as whatever you want, but just remember, when calculating E3 for example, and if you're labeling them as 1 2 3, you should calculate the expected value for this cell, not this cell. Okay, so make sure you calculate the expected values according to what you label them. I've labeled them row by row, you can do column by column. Okay, now that we've calculated the expected value, now we need to calculate the test statistic. This is denoted by another formula, which is the test statistic, which is T is equal to the sum of values I equals to 1 from sample size n, and in the formula we have here observed value of I minus expected value I, then we open and close brackets. So we find the difference between the observed and expected value, we square that difference, and we divide it with our expected value I. Okay, so this formula is going to be the one that we use to calculate the test statistic. Now this formula only holds when every single expected value we've calculated here is greater than 5. In this case, well, all the expected values are well above 5, so we need not worry about combining any rows or columns. Okay, now to calculate the test statistic, using the formula we can just plug in our values. So when I equals to 1, we have here observed value of the first one is 72. Which is the observed value of the first one minus the expected value, which is 61.425. We whole square the difference between our observed and expected and divide it with our expected value itself. Okay, moving on, let's plug this into the calculator. 72 minus 61.425 whole square divided by 61.425. Okay, so now you can calculate the value for this, but just note that it's going to be more difficult to calculate all the test statistic because we need the exact value. So I'd suggest just keeping it into the calculator for now. Next, when I equals to 2, our observed value becomes 2, which is 42 here. Let's open up the bracket. Yeah, 42 minus it with our expected value, which is E2, 44.46. Now using the difference between the observed and expected, both square it, divide by the expected value. Right, so let's plug this in the calculator, which is 42 minus 44.46 the whole square divided by 44.46. Right, next up, when I equals to 3, our O3 is 52. Our expected value is 54.405. Find the difference, square it, or divide by our expected value of 54.405. Okay, moving on. Now that we've calculated the expected value, now that we've calculated this for I equals 1, 2, 3, we go on for 4, 5, 6, 7, 8. It's a long and tedious process, but it is not complex, which is much better than more other questions. So 52 minus 54.405, then whole square divided by 54.405. Okay, moving on. I equals 4, so our observed value becomes 68. Our expected becomes E4, which is 73.71. Right, we find the difference between the two, square it, then whole divided by our expected value itself. Okay, so we've calculated the values for 4. Now for 5. Before I proceed to the fifth one, let's just plug this into the calculator. 68 minus 73.71 whole squared divided by 3. Okay, it's very easy to make errors when calculating this, so do be careful when doing this. Next we have here O5, which is 33. When I say O5, I mean that when I equals to 5, we have O5 minus E5 by E5. So yeah, O5 is 33 minus the expected value 5, which is E5, which is 43.575. And we find the difference between the observed and expected, whole square the difference as before, and we find expected, divide by expected value. Okay, so we found for the first 5 values. Moving on to the 6th. Before I start, let's put this in. 33 minus 3.75. Also do note these extra brackets are not needed. I just do that so that it's more easier to differentiate between our values, like when is I equals 1, I equals 2. It just makes it much easier to differentiate. Divided by 43.575. Okay, so now that's equal. Let's move on to I equals 6. And I equals 6, our observed value is 34. Right, so 34 observed value minus that with our expected value of 31.54. Whole square that difference, and then whole divide with our expected value 31.54. Right, plug this in the calculator, which is 34 minus 31.54 whole squared by 31.54. Moving on with I equals to 7. When I equals 7, our observed value becomes 07, which is 41. 41, this is a bracket, not 141. Minus it with expected value, which is 38.595. Yeah. And we whole square the difference as before and divide by expected value. That's when I equals 7. Let's put this in calculator once more. So 41 minus 38.595 whole square divided by 38.595. And then finally when I equals to 8, when I equals 8, we have our absurd value as what is it? Yeah, 58. Minus that with 52.29, so this 52.29 whole square the difference between the two, and finally we can divide it with our expected value. Okay, so this is how we calculate the test statistic. Very tedious, but it is how it is. So 58, let's write this in here. Okay, so looks like we've reached the limit to which this calculator can put in more functions. Yeah, okay, so I'm gonna add this last part after we've calculated the total of this. So let's just go through everything so that we've got the right values. So far it's okay. Moving on to this, when I equals 2, I equals to 3 now coming up. When I equals 4, I equals to 4. Now when I equals 5, it's okay. Moving on, when I equals to 6, I equals 7 coming up, fine. When I equals to 8, it is not there just yet, so we've got our test statistic as 5.41 plus the remaining one right here, which is 58 minus, oh wait, let's open the bracket once more, 58 minus 52.29 whole square the difference and then divide with 52.29. so the number of terms can get quite long, so we may have to break up our results in two. And we have here a test statistic as 6.037. so that means t is equal to 6.037. okay, that's good. We found our test statistic as 6.037. okay, next thing that we need to do is find the critical value, because whenever we're doing a test we need the critical value and the test statistic. These are the basics of every single test that we do. And to find the critical value, let's use the space given here. We need to find two things, which is the p-value and the Greek letter nu, which represents degrees of freedom. So we have here the x squared or chi-squared distribution. We need to find the p-value, which is the column headings, and the degrees of freedom, which is the row headings. Based on the intersections of the two, we can find our critical value. So what exactly is going to be our critical value, you may ask. Fine. So to calculate the critical value, first let's find the degree of freedom. Okay, and that is equal to number of rows minus 1 multiplied by number of columns minus 1. So if you remember how the table looks like, when you're considering only the values that we use to calculate the test statistic, basically all the values here which we've labeled from 1 to 8, these values, this is considered our table. We don't consider anything else. Number of rows 1 2, number of columns 1 2 3 4. So we can put here 2 minus 1 times 4 minus 1, which is equal to 1 times 3, which is equal to 3. So you've got 3 degrees of freedom. Next, to find the value of p, and p is equal to 1 minus alpha, because whenever in a chi-square test we don't ever have a two-tailed test, so we're going to consider 1 minus alpha. Okay, but alpha is the percentage value, so 10%. So at 10% alpha will be 0.1, so 1 minus 0.1 is 0.9. This is when alpha equals to 10%, and 10% is the equivalent of 0.1. So that gives us 0.9, or put 0.90 because of the p-values. And now how do we reference the critical value? We're going to write here the guy's x squared, and in the lower exponent here we're going to write here the degrees of freedom 3, and then we're going to open up the bracket and write 0.90, which is the p-value. And this, when you do this right here, we find a critical value. So at degrees of freedom 3 and 0.9 as the p-value, we can have an intersection at 6.251. So our critical value becomes 6.251. Now that we have the critical value and the test statistic, all that remains is to compare and conclude. So now that we found the tabular value, critical value, right, we need to compare. So we have our test statistic as 6.037 as shown over here, and we have the critical value, which is 6.251, and the critical value is greater. So when we have a critical value greater than the test statistic in a chi-squared test, we accept H null. If not, we reject. So in this case we accept H null. Okay, so when we say that, when we accept H null, there's a certain structure that we follow in our answer, which whenever we accept H null, we say there is insufficient evidence to suggest that, and then we put in our alternative hypothesis, which is success in driving test is dependent on the distance structure. So there is insufficient evidence to suggest that the success of the driving test is dependent on the instructor. There is insufficient evidence to suggest that the success of the driving test is dependent on the instructor. So this right here is the answer, the final conclusion. And moving on, we have here continuous random variables. Okay, this should be relatively simple because we only have one function, that is 1 by 81 times x squared. So to find the expected value of the root x right here, we have the CDF. Do note this is called the CDF, which is cumulative distribution function. And now we need to find the PDF first. First we need to find PDF. So to calculate PDF, we just need to differentiate this function right here. So whenever we find PDF, we note that PDF is represented as the lowercase f, and this is equal to the differentiate of this. How do we differentiate this? Well, it's going to be 2 times 1 by 81, and our exponent decreases by 1, so it's going to be 2 times 81 multiplied by x. Okay, now that we've differentiated this, I think we can also state the ranges, so just for a little extra detail, because sometimes they may just charge a mark if you don't do that. So right here, and we can write 0 otherwise. So what we've done right here is just written our PDF function for the CDF above. Okay, now to calculate the e root of x, we just simply need to integrate this function, but we need to multiply root of x with it when integrating. So to integrate 2 root 81 x, and right here we will have the limits, which is 9, our upper limit here, and 0, which is our lower limit, which is right here. And these are our lower and upper limits. This is a function we have, and we need to multiply this function with root x, and root x is equal to x to power 1 by 2. So when we're multiplying x to power 1 by 2, this x over here multiplies with this. So the law of indices or law of exponents states that am times an equals to am plus n. Similarly, when you multiply x, which is represented as x to the power 1, and x to the power 1 by 2, we have here a to the power of, or x to the power of 1 plus 1 by 2, which is 3 by 2. 3 by 2. So using that simple law, we can find out that the exponential power is 3 by 2. It isn't really necessary to show the calculation over here, but this is just for understanding. You can actually go directly into this equation, and we have to integrate this with respect to x. Okay, so don't forget the dx here, and we can factorize out our 2 by 81 because it is a constant that doesn't need to be integrated. And now we can go back to integrating 9 0 x to the power 3 by 2. Okay, so when integrating, we can get, first we need to write with respect to x. It's not something we can forget. So dx, don't forget that. So 2 by 81. Right, so to find the integral of x to the power 3 by 2, we can just add 1 to this exponent, which is x to the power 5 by 2. And given that the coefficient is 1 over here, the fraction over here multiplied by 5 by 2 equals to 1. So it's just going to be its reciprocal, 2 by 5. X to the power 5 over 2. The limits 9 0. Okay, now this is the very statement that should basically conclude and find the value for e root x. We plug in our limits. Okay, we plug in the limits. When you put in x equals 9, we subtract that with x equals 0, and just to save us some time, when x equals 0, this entire thing becomes 0, so there's no point of subtracting with it. So we can just put right here 2 by 81 multiplied by 2 by 5, 9 multiplied by 5 over 2. This is all that you need to put. We can put minus 2 by 5 with brackets 0 to the power 5 by 2, but it doesn't change the value one bit, so you shouldn't really need to emphasize on things that don't matter. So calculating this, we get so when we calculate this value right here, we can get 2 by 81. Let's just plug this in calculator. So 2 by 81 times 2 by 5, 5 multiplied by 9 to the power 5 over 2. Close bracket, we get 12 over 5. Okay, and we can put it in fractional form, but whenever we're finding e root of x or any kind of variance or anything, they expect in decimal form. So let's write e root x is equal to 2.4. I think it's 2.4. Yeah, it's 2.4. Okay, moving on. Now that we've done this question right here, just box it up. We have to find the variance, just as I've said for the other one. Okay, to find the variance, this may be a bit tricky, so I'm going to provide you the formula that you must know. So to have here variance of x, this is not root x, just x. Okay, and is equal to the e of x squared, e of x squared bracket minus e of x the whole squared. Okay, so using this formula, we can derive that when we have variance of root x, we just put wherever we have x over here with root x. So variance of root x equals to e of x minus e of x over here is 2.4, so we just put minus 2.4 e root x. Okay, we do minus e root x and we square that value. Okay, so all that we need to have is ex to find the value of variance. So to find ex, just as we found e root x by multiplying it with 1 x to the power 1 by 2, we just multiply this with x itself. So 2 by 81 x squared now. So now we must integrate 2 by 81 with limits 9, 0, x squared with respect to x, and this is equal to 2 by 81 multiplied by, and now we put here, when you integrate you get x cubed over 3, and once again we need to plug in our limits when x equals 9 and then minus it with x equals 0. But just to save us some more time here, when we put in x equals 9 we get a value, but when we put x equals 0 we get no value, so subtracting it would have no effect. So right here we have 2 by 81 multiplied by 9 cubed divided by 3. So let's just calculate this value here. That's going to be 2 by 81 bracket 9 to the power 3, divide this by 3, and this is going to be our ex, which is equal to 6, exactly 6. Okay, so now we have our ex, and this can be used to calculate our variance. So we can have here variance. Okay, and that's, I'll denote this in a different ink. So here the variance of root x is equal to 6 minus 2.4 squared, which is equal to 6 by 25, which is 0.24. That's our variance answer. Okay. Yeah, that should be it. And for the last one, when y, okay, random variable y is given with y cube equals x, find the PDF of y. So we can't just plug in y cube into our PDF. We need to actually plug y cube into our CDF and then differentiate it, and then we can get our PDF. So whenever we have the random variable y, CDF changes from f of x to g of y. Okay, and it's going to be capital G. So let's write our CDF for this. Okay, we have a lot of space for this. So g of y is equal to, right, so for the first one we have 0, that stays 0. This is applicable when x is lower than 0. So when we have x is lower than 0, we basically have y cubed lower than 0. And when you solve this inequality, it doesn't matter, it's just going to be y lower than 0. So we can just erase the exponent here. Let's just put this a bit more adjacent towards it. So yeah. Okay, moving on. Now we need to plug in the values of x, and right, just put this here. Okay, moving on to the function. Now we have 1 by 81 x squared. 1 by 81. When you have x squared, you're basically doing y cubed, which is x squared. This is just when you apply the law of, this is a to the power m whole to the power of n, it is equal to a to the power of m times n. Using the same law of exponents in this, you can get 1 by 81 multiplied by y to the power 6. Okay, so have here y to the power 6. Okay, now to find the range. To find the range of the PDF, of the CDF, this is applicable when x is between 0 and 9. So let's solve the first inequality. It states this, right? This is the range that it said. So let's first solve this. and this is the equivalent of y cubed. So whenever we have 0 over here, it really doesn't matter. It's just going to be y greater than 0. So yeah, y is going to be greater than 0. Okay, so let's just plug in our value for x as y cubed. So far in our equation, we've got y is greater than or equal to 0. And next we have y cubed is, okay, let's write this separately. Y cubed is lesser than or equal to 9. So y is going to be lesser than or equal to the cube root 3 of 9. This is going to be the upper limit of our function when you have y in this thing. Okay, so we have here the range for y, which is, yes, this is our range that we need to write. This is important when we write our PDF. Okay, normally they'd expect us to write our PDFs also with this range, although they just want to see the CDFs with this. So it's not very important to write it, but it's out of free will. Okay, moving on, now we have the range. We have to write 1 when y is going to be greater than, which is just the upper limit of this, which is going to be y is going to be greater than cube root of 9. Okay, now that we found the CDF of the function y, we need to find its PDF. To find the PDF, we just need to integrate the function. Okay, so we have here, and you should notice that PDFs don't have the 0 and 1, they just have a 0 after the function, and in the ranges they just write otherwise as stated over here. This is the CDF, so same as here, we just replace with 0 otherwise. Okay, so what's the function going to be when differentiated? It's going to be 6 by 81. So let's simplify that. 6 by 81 multiplied by y to the power of 6 minus 1. So that is 2 by 27 multiplied by y to the power of 5. And this is applicable when the range is the same as a CDF, which is, yeah. So you can choose when to solve for the ranges. It doesn't really matter. They won't assess you based on the PDF. They only assess you based on CDF. And over here we had to write 0 otherwise. Right, so that is pretty much all that is for continuous random variables. Moving on back again into inferential statistics. Alright, this is an 8-marker question. Carry out a test at 5% significance level to test the null hypothesis, the mean of A equals B, against the alternative where it states the mean of A is not equal to B. Okay, so immediately we can identify this is a two-tailed test. So it is good to note that our significance level will become 1 minus alpha by 2, where alpha equals to 5%, or it can be 1 minus alpha over 200. Okay, so let's just calculate the p-value. So p is equal to 1 minus 5 by 2, which is 1 minus 5% by 2. So it's going to be 1 minus 5% is 0.05 by 2. That's equal to 0.975. Just to keep note of our p-value. Okay, so that means that our p-value will either be in this region right here, this column right here, or our p-value could just be 1.96 depending upon if you're taking z or a t-value. Okay, let's erase these formulas. Okay, moving on. So whenever we're doing testing, the basic steps are to find the test statistic and the critical value. Then we have to find, for the test statistic, we need to find the formula. And the formula, first of all, the test statistic can be represented with the letters Z or T. So how do we know if it's 0t? That's where we look at the sample size. So let's just state the sample size of each of these. Number of x terms equals to 50. Number of x meaning region A. So 50. And number of y terms, which is from region B, equals to 60. Okay. So with this data, we can confirm whether this is a t-test or we need to use the z values. So which one do we use? It's simple. So when we have such large samples like 60 and 50, our degrees of freedom won't be applied over here. We can see that the degrees of freedom will be this nx plus ny minus 2, because there are two parameters that we are calculating. So we have here 110 minus 2, which is 108. It's nowhere to be found here because there's no degree of freedom of 108 written here. So you can move to over here, right here, not this here, here. So we don't need to find the degrees of freedom for this question. All we need is the p-value, and we've calculated the p-value as 0.975. So we know that our critical value is going to be this 1.960. Okay, so first let's give the formula. Z is equal to the, okay, this is going to be the x mean minus the sample mean of y whole divided by root of S2. Note that sometimes I have S2 divided by the number of terms, and sometimes I have root of S2 like shown over here. There is a difference by what this means, because in S2 for this S2 we are using the combined estimate of two samples, so we don't need to divide it by the number of terms. When we did over here right above this question right here, we did root by S2 divided by number of terms over here. That's because we're doing a single sample test. So just to clear any confusions that are raised from this. Okay, so with this formula we need to see what values we have. We don't have mean x, we don't have mean y, nor do we have S2. So let's calculate each of these values. So we can calculate mean x and mean y, very simple. That is just the sum of x values divided by number of x terms. So sum of x values divided by number of x terms, which is 282 by 50, which is 5.64. 0.64. Next we have mean y, which is equal to sum of y terms divided by number of y terms. Sum of y terms being 328 divided by 60. So that's going to be 82 by 15, which is 5.6 recurring. Okay, so I'm going to write this in the fractional form first. 82 by 15. Okay, and this is equal to 5.47. Let's keep it to 3 significant figures. Okay, whatever it is, sample mean of y is lesser than sample mean of x, so we're not going to get a negative z value. Even if we did, it wouldn't matter. Okay, moving on. Now we need to calculate S2. To find S2, there is a formula when we have a two sample test, by the way. So space, fine. So when we have a two sample test S2, and do note we're not using S2P because nowhere does it say that the population variances are equal. When I say S2P, it means the pool variance. There is no need to use pool variance, which is this, as you may have seen in some questions like this. This is pool variance. We don't need this because the population variances are not assumed to be equal. So we use the normal S2 formula, which is S2x by number of terms of x plus S2y divided by number of terms of y. Okay, so using this formula, what values do we have? We have nx, we have ny. We don't have S2x, we don't have S2 of y. So here's where it gets a little bit more simpler. So we have here S2x to calculate and S2y. S2x and S2y have the same formula to calculate, except that we use the corresponding sum x squared, and sum y squared. So over here we can write a formula. S2x is equal to 1 divided by number of terms of x minus 1 multiplied this with sum of x squared minus sum of x the whole squared divided by number of x terms. This is the equation that you must follow for S2 of x, and same can be said for y, except wherever you see x we just plug in the values of y. So over here we have 1 divided by number of x terms is going to be 50, so 1 by 49, and we multiply this with sum of x squared 1596 minus with sum of x the whole squared, which is 282 the whole squared, divide this with the number of x terms, which is 50. And this is how you calculate the S2 of x. So let's put this into the calculator. 1 by 49 multiplied by 1596 minus 282 squared divided by 50, and this here is our answer, 138 by 1225. This is the S2 of x value, which is a very long value. So I'm just going to write here, which is equal to 0.11265. Just keep it to this many significant figures, no need to go too specific on it. And similarly we need to calculate for S2 of y. So you can use the same formula as above, except replace x with y. So we have here 1 divided by number of terms of y minus 1, which is 60 minus 1. So I'm going to use this equation here, and number of y terms becomes 59 here. Actually let's just write this here first. 59 multiplied by sum of y squared is 1808, and this is subtracted with minus 328 whole squared divided by number of terms of y, which is 60. Just like that we'll find our S2 of y. So just plug in the values. Okay, minus 328 squared by 60, which is equal to 224 by 885. So 224 by 885, which is equal to 0.25311. 311. Okay, we found our S2 of y as well. Now our formula becomes accessible over here to find S2. So how do we find S2? Just plug in the values. S2 is equal to, and I'm just going to plug in the values, no need to reference each value here. So S2 of x, this is where the fraction comes important. So S2 of x we've noted as 138 by 1225, and when we are dividing with nx, all we're doing is multiplying the denominator with nx, number of terms of x, which is 50, and this is added on with S2y, and I'd like to use the same format as before. 885 multiplied this with the number of terms of y, which is 60, and this becomes our combined estimate formula, which is our value. So it's 0.00647. Right, so 6472 is the S2 value, and now we just need to plug this value into our final equation. So let's carry this out. Z equals to x mean, which is 5.64, minus this with 5.47. Do note we are using the fractional value for this. Whole divided with root of 0.00647 is equal to, now let's do this, 5.64, which is our sample mean of x, which we got a neat value for, but the sample mean of y we didn't. So we're just going to put in 82 over 15. Just for a surety, you can put 328 over number of terms, 60, which should be the same thing. Okay, and this is divided with the root of answer being the S2 value we've calculated earlier, and that's going to be 2.1545, 1.5466. So it's going to be to 4 significant figures, because each value in the critical value table is in 4. So it's going to be 1.2.55. Now we found our critical value to be, the critical value is, what's the critical value? It was 1.960. So now we just compare 2.155, which is the test statistic, is greater than our critical value of 1.960. So when our test statistic is greater than critical value in inferential statistics, we reject H null. Right, so we reject H null, and when we reject H null, there is a specific structure, which is there is sufficient evidence to suggest that. Now we insert our alternative hypothesis. So our alternative hypothesis was the mean of A is not equals to the mean of B. So saying that the means are not equal, so that means are not equal. Okay, so we can just insert the alternative hypothesis. Okay, moving on, we have here a Wilcoxon signed rank test, and let's just solve the values. Okay, so for the first question, it states give a reason why a Wilcoxon signed rank test is more appropriate, or may be more appropriate, than a t-test when investigating whether there's any evidence of preference of one of the uniforms. Okay, so whenever we're doing a t-test, as stated, we must know that the assumption above, which is stated here somewhere, yeah, for this inferential stats based question, we need to know that the population is normally distributed, or the underlying data's distribution is normal. When we're doing a paired t-test, we don't talk about the data's distribution. In fact, we talk about the differences distribution. So we need to know that the underlying data must, the underlying population differences must be normally distributed. Okay, so we don't know whether this is true. So how we frame the answer for this favoring Wilcoxon signed rank test is that say that underlying population differences must be normally distributed. This cannot be this, or this isn't assumed above. Right, so this is a way you can write the answer. Moving on, carry out Wilcoxon match pairs signed rank test at 10% significance level. Okay, so before we do any test, we state our hypothesis, and so far we've mostly been given our hypothesis. This time we have to write it ourselves. So H null states that the population medians are equal, which means M1 or MX, we'll consider it as MX equals to My, which is population median of Y. You can write this in words, but I like writing it in symbols. They do not cut any marks for writing it in symbols. And we can write MX, and now this is where we have to look whether it's greater than, lesser than, or just not equal to. Says here whether there is evidence of preference for any one of the uniforms, meaning mx can be greater than or lesser than. So we're going to say that differences of the population medians, there's basically no difference, or not equal to, no difference. So here it's just not equal to each other. One is given more preference than the other. These are our hypotheses. Okay, moving on, we have moving on. So whenever we have a sign rank test, we need to calculate the differences for each of these. So let's calculate the difference. We're going to do uniform x minus uniform y for each of these. So for the first one is 82 minus 78, which is just positive 4. Next up we have 74 minus 75, which is negative 1. Then we have here 42 minus 63, which is negative 21. Okay, moving on, we have 59 minus 56, which is positive 3. Then we have negative 7 for this. 73 minus 82 is going to be negative 9. This will be negative 5. 98 minus 90. Remember, we're just subtracting the top value minus the bottom value. That's what we're doing. 62 minus 72 is just negative 10. And this is going to be negative 12. And finally, we have negative 11. So we found the differences of each of these values. So let's just keep this here. I'm going to call this differences. Okay, now let's take the now we have to rank them. Okay, so in order to make it as easy as it is to understand, we're going to take absolute value of differences. Let's just take absolute differences just so that I can fit it in here. And I'm going to just can't copy this. Okay, fine. So what's the absolute values? 4. Then we have here 1, 21. We have here 3 remains 3. This becomes positive 7, 9, 5, 8, 10, 12, 11. Okay, now that we have the absolute of differences, now we're going to put ranks. Okay, so what does it mean to rank? It means that we're going to be assigning a number from 1 to 11 to each of these ranking. The reason I say 1 to 11 because that is the sample size, n equals 11. So as simple as it is, we're just going to be ascending. We're just going to arrange everything to ascending order and then give them ranks between 1 to 11, with 1 representing the lowest value and 11 representing the highest. So ranks are going to be, let's write this in this. Okay, ranks. So for the first one, when the rank is 1, the lowest value becomes 1 here. Then the next lowest value is 3. Remember, we don't take science into consideration just yet. Then 1, 3, 4. Then we have here 5, which is, do not confuse between the 3 here, 4 here. We're just ascending order them, so don't confuse yourself with this. We have 5, 6, 7, 8, 9, 10, 11. So now all you need to do is just check, have you ordered everything correctly? And in this case, I have. Okay, now we're going to do something called signed ranks. So what does it mean to do a signed rank? Ranks. Signed ranks is basically we're going to take into consideration the differences. So if it's a positive difference, we get a positive rank. So in the first instance, our rank is 3 and our difference is a positive 4. So our rank becomes a positive 3. The second example here, we have a rank of 1. Our difference is negative 1. It's a negative value, so our rank becomes negative 1. So this becomes negative 11. this becomes 2, this becomes -5, this becomes -7, then -4, this is a proper 6, this remains as it is. Then we have here -8, and do note why I'm getting the negative value, because the negative difference, we just correspond that with the rank to get negative ranks. -10, -9. Be careful not to write differences with this, because you may be confused, because they're well within the range of the sample size. Okay, now what we need to do is calculate P and Q. What is P and Q? Well, that represents the positive ranks and the negative ranks combined. So the positive ranks is 3 plus 2 plus 6. This is the sum. So we need to add up all our positive ranks. I don't need to specify this. So let's put 3 plus 2 plus 6, which is 11. Okay, so just by looking at it, you can see which is going to be the test statistic, but I'll explain that later. Now we need to find the, let's take green. Okay, yeah, now we need to find the Q value, which is the sum of all the negative ranks, which is -1, -11, -5, 7, 4, 8, 10, 9. Okay, so how do we find this? Just add them up. 11, 5 plus 7 plus 4 plus 8 plus 9 plus 10. Or you could use a summation of series formula and put sample size as n equals 11 and put 11 times 11 plus 1 by 2, which gives you 66, and that should be the sum of all the values from 1 to 11. And given that P equals 11, Q equals to 66 minus 11, which is 55. So it makes calculation all the more easier. Okay, now I'm going to write the formula to calculate the test statistic. T is equal to minimum of P comma Q, which is equal to the minimum of 11 and 55. This is obvious, it's 11. Sometimes by looking at the number of positive values and negative values, you can see which is the test statistic. It is 11 in this case. Therefore, our test statistic becomes 11. T equals to 11. Okay, now we need to find the critical value. Okay, so we're calculating at the 10% significance level, and this is a two-tailed test. So two-tailed at 10% significance level. Let's go to the test here. A two-tailed 0.1. 0.1 representing 10%. Okay, so two-tailed 0.1 for a sample size of 11 is 13. N equals 6, meaning sample size, and 13 is our critical value. So we have here, we can write critical value from tabular column is equal to is 13. Okay, now that we have this, we can get to our conclusive statement, where we compare the test statistic and the critical value. 11 is obviously lower than 13. So what do? Okay, this is a non-parametric test, which includes signed rank test, Wilcoxon matched pairs, and any non-parametric test. Wherever you have the critical value greater than our test statistic, we reject H null, as stated here. It's just the direct opposite of inferential stats. Think of it as inferential statistics. When the critical value is greater, we accept H null, but whenever it's non-parametric, we just do the opposite, and the same goes vice versa. So when we reject H null, the structure for accepting H1 goes like this. So that is sufficient evidence to suggest that, and now we write our H1, which is mean X is not equals to mean Y, which means that population means are not equal, or we can write preference for one of the uniforms. So there is sufficient evidence to suggest that there is preference of for one of the uniforms, uniforms, right? So this is the conclusive statement to our Wilcoxon signed rank test. Lastly, we have PGF, and yeah, that should sum up the paper. Fine, to do PGF, very simple. Let's first read the question. Okay, so there are 4 red balls, 2 blue balls, so total of 6 balls. Tanji collects 3 balls, okay, without replacing them. Okay, without replacement is key, and this is very important. The number of red balls selected is noted by X. Find the PGF of Gx of T of X. Okay, sure. Very simple. So to find the number of red balls selected, when we take 3 balls from a bag, what is the maximum number of red balls we can collect? Given that there are 4 red balls and 2 blue balls. Maximum number of red balls is 3. Minimum will be, well, at least 1. We are calculating. We would get at least 1 heads. Right? So the probability of getting 0 heads, how is that possible? Because if there are 2 blue balls and he collects 3 balls, even if we take the first 2 balls as blue, in the third pick, all 4 balls are red balls. So we're definitely getting a red ball. So the probability of getting 0 reds is 0. Okay, now the probability of getting 1 red. Okay, so to get 1 red, it would mean that you either pick 2 blue balls in the beginning and then you get a red ball, or you pick a blue ball, then pick a red, and then pick a blue, or we can pick a red ball in the first and then pick 2 blue balls, and this can be denoted with the probability as 4 by 6, the first one, and then picking up blue balls, so 2 by 5 multiplied by 2 by 5, no, multiplied by 1 by 4. Okay, so this is the probability of getting that in the first one. Now we can multiply this by 3 because all we do is just shift the probability of getting red by 3, so this becomes 1 by 5. Okay, also getting 2 reds. We can use the same thing, however using that method can be a little bit error prone. So I'm going to go straight to 3 reds and I will show you how to do for 2 reds immediately. For 3 reds, you would have to get the odds of getting a red in the first is 4 by 6. Then the total number decreases to 5, and total number of red balls is 3, total number of balls here, and 2 by 4. This is the probability of getting a red, all 3 red balls, which is 20% or 1 by 5. Now you should note that all the probabilities will sum up to 1. So 1 minus 1 by 5 minus 1 by 5 equals to 2r. The probability of getting 2 reds, which is just 3 by 5. We can use it by calculating the normal probabilities, but it's going to be more error prone. Okay, so now t will be to the power of whatever we have here. Okay, so this means that t will be to the power of 0 here. This is t to the power of 1, which is the same as t. This is just the same as t. This is t to power 2, and this is going to be t to power 3. Okay, these are just the coefficients for the probabilities. So the final answer will be gx of t. This is how we write our PGF. And this is equal to 0 times t to power 0, which is just 0. Then we have 1 by 5t plus 3 by 5t squared plus 1 by 5 t cubed. Okay, so these are our probabilities. This is the final answer. Okay, but if you look at the question here, it's a bit of planning ahead. You will see that the PGF of Z is the number of red balls selected by Tanji and the number of heads obtained, which is PGF of Y, which means we'll have to do some multiplications of polynomials. So to make this much easier, we can factorize 1 by 5t out of this entire equation, and we have 1 plus 3t plus t squared. This is the same as the above one, except we've just factorized it. We should write the above one as a final answer, but factorizing this will give us an easier value to calculate to get this PGF of Z. Okay, so just verifying if what I factorized is correct. In this case it is. Okay, Now Tanji throws also has 2 coins each buy, so the probability of obtaining a head is 1 by 4. Okay, so you don't need to worry about replacement because you don't need to replace anything. And he throws 2 coins at the same time. The number of heads obtained is denoted by y. Find the PGF of GYT of y. Okay, so given that the number of heads obtained is denoted by y, we have to find the probability of getting 0 heads, 1 heads and 2 heads. So probability of getting 0 heads. Okay, so how do we find the probability for that? It will just be 3 by 4, which is the probability of obtaining a tails, and multiplying it again by 3 by 4, which is another probability of getting by tails, which is 9 over 16. Okay, that's 0 heads. Next we have 1 heads. Okay, so for 1 heads, how do we obtain 1 head? So it will to get 1 by 4, getting a head in the first coin, getting a tail in the second, and this is also going to work in the reverse order, so we can multiply by 2, getting a tail in the first and head in the second. So we have here 3 by 8. 3 by 8, I'm going to simplify it, not simplify, I'm going to keep it to 6 over 16. Okay, we want to keep everything with a common denominator. And at last we have 2 heads. Odds of getting 2 heads is just 1 by 4 multiplied by 1 by 4, which is 1 by 16. So yes, now I can just factorize 1 by 16 out of it. But when we are writing an answer, we should not factorize. They don't expect us to factorize, so we will not factorize. Is equal to t to power of 0, which is just 9 by 16, plus 6 over 16 when t is to the power of 1 over here, so we can just write t, and over here we had it with 1 over 16 when t is to the power of 2. Okay, now this is our final answer, so let's just keep it in a box neatly there. But the next question would require us to multiply our two polynomials, so let's factorize. So we can get 1 by 16 factorized here. Factorize 1 by 16, we get 9 plus 60, 9 plus 60 plus t squared. So let's just verify if our factorization is right. In this case it looks like it's good. Yeah, this is the factorization. Let me just make this a bit more clearer. So the random variable z is the sum of red balls and number of heads, and the PGF of z. So GZT is equal to GXT. Whenever they say it's a sum of two different PGFs, you need to multiply the two PGFs. GYT. Okay, now to multiply the two of these, we're going to take our factorized form because that's going to be much easier to multiply. So we have here 1 by 5t multiplied this with 1 plus 3t plus t squared. I think that is what I wrote. Yeah, multiply this with GYT, which is 1 by 16, and we multiply that with this here. Okay, so we have, okay, so we can simplify things a bit easier, so we can multiply these two over here. So 1 by 5 times 1 by 16, I think it should be 1 by 80, but just to verify, yeah, 1 by 80, 1 by 80. And don't forget we've multiplied this with t as well, And now we have to multiply the two polynomials here. So using FOIL method, we get 1 times this entire thing. So we just copy down our formula, 60 plus t squared. Okay, next we have 3t multiply this. So 3t times 9 is equal to 18t. No, sorry, it's going to be 27t. Okay, 3t multiplied by 6t is going to be 18t squared. So let's add here. And finally 3t multiplied by 3 squared t squared equals to 3t to power 3 3t cube. Okay, this is added on when you multiply t squared with each of these, so it's 9t squared. So 9t squared plus, when you multiply t squared with 60, you get 6t cubed. And now we have t squared times t squared, which is just going to be t to the power 4. Okay, so we've done that. Now we can simplify our equation. Which is going to be 9 plus 60 plus 27t, so that's going to be 33t plus t squared plus 18t squared plus 9t squared, which should be 28t squared. Now we have to add up all the t cube coefficients, which is just 9, and then we have t to the power 4. Okay, so this is our entire equation right there. This is the probability generating function of z, but we need to follow the same pattern as we've done for these. So we need to express this in fractions. So gz of t is equal to 9 by 80. It's best to keep them all as factors of 80. We don't need to simplify these. So yeah, 9 by 80t plus 33 over 80t squared. All we're doing is multiplying t by 80 with each of these, and we get here 28 over t cubed. 28 divided by 80t cubed. Add this on with 9 divided by 80 times t to the power 4. Finally, the last one, 1 by 80 divided by t to the power 5. Okay, this is our simplified equation. Use the PGF of z to find Ez and variance of z. Okay, to find Ez, very simple. I'm going to show the formula. So it's E of z equals to the probability generating function of z when differentiated, and you have t equals to 1. So let's first find the So let's first find the PGF of z itself. PGF and differentiated. So that's going to be denoted as like this. It's equal to. Now we just need to differentiate. So yeah, when differentiating, we get this stays as 9 by 80. So 9 by 80 times plus 66 over 80 t plus 28 times 3. So that's going to be 28 multiplied by 3, which is 94. By squared, the exponents decrease by 1. 9 times 4 is just 36. T to the power 3, and 1 by 80 times 5 is just going to be 5 by 80. Once again, we don't really need to simplify any of this. 4. Okay, now we just need to plug in t equals to 1. When you plug in t equals to 1, we are just adding up the coefficients, because 1, 1 squared, 1 cubed, it's just still going to be adding up the coefficients. So let's put in this here as gz when is equal to ez, which is expected value of z, which is equal to 9 by 80 plus 66 over 80, or you could just factorize 1 by 80 out of this entire equation and do it, which would be much easier. But either way, we just need the answer, and both ways grants us the correct answer, so stick with this. 5 by 80. Over here we get our answer 2.5. 2.5. This is our EZ. Okay, and now to find the variance. To find the variance of Z value. To find variance of Z, how we do this? So this is going to be a bit more complex, but it is just as bit as doable. So gz, now we need to double differentiate and plug in t equals to 1, and similarly we're going to add up our ez, which is gz dash 1 minus gz dash 1 but whole squared. Okay, so we have gz dash 1, so we just need to find the double differentiate of the pgf of z, and that can be done very simple. So I'm going to factorize our earlier function. So okay, let me just factorize the first function so that our value becomes much more simpler to calculate. gz of t, I'm going to factorize 1 by 80 out of this. We have 9 plus 66t plus 84 t squared plus 36 t cubed plus 5 t to the power 4. All I've done is factorize so that our differentiating will be easier. Moving on, let's double differentiate this value, and given that it's a constant, we don't need to differentiate 1 by 180. And when you differentiate 9, you get 0. When you differentiate 66 to t, it's just going to be 66. 84 times 2 is going to be 168. So 168 multiplied by t plus 36 times 3, I think this is 108, yeah. T to the power 2 plus 5 t to the power 4 become 20 t to the power 3. Okay, now to find gz double dash 1 is equal to 1 by 80 multiplied by 66 plus 168. Once again, we're just adding up the coefficients. 168 plus 108 plus 20. We get this value as 1 by 80 plus 66 plus 168 plus 108, finally plus 20. And this should give us a value of 181 over 40, which is 4.525. Okay, now finally we can plug in our values and get the variance. So variance of z equals to 4.525 minus 2.5, no wait, plus 2.5 minus 2.5 squared, so plus 2.5 minus 2.5 squared, which is equal to 31/40 or 0.775. So our final answer, E of z equals to 2.5, variance of z equals to 0.775, and just box this nicely, and there you go. That is the end of this paper. I hope you've understood all the concepts that's used into this paper well. I hope you enjoyed the video as well. Please ensure to like, share and subscribe, and I will see you in the next video. And this has been probability statistics of the May June series 2021 paper 4142. Thank you for watching.